So let's start by asking the question of what is the variance of random chance? Well, what element of difference should be driven by random chance? Well, we have four groups here. Now, the variance between the groups is partially random chance, but could also be the effect of the measurement, right? Low depression, low anxiety, and high depression, high anxiety might be different because of random chance, but they also might be different because of the depression and anxiety levels. So the between variance doesn't really account for it. But however, everybody in the low depression, low anxiety, everybody within a group should have a similar amount of a variable, similar amount of sleep. And the difference between the individuals within our group, the variance within our group, is actually probably due predominantly or exclusively to random chance. All right, so the difference between all 50 people in the low depression, low anxiety is due to just random sampling effect. And the difference between the people only within the high depression, high anxiety is due to random sampling effect. That's true for each group. So the within group variance, the variance within just one group, is a good metric for random chance. So the first step in the ANOVA is to solve for what we call the within group variance, the variance within the groups. And we're going to do that the same way we have always solved for variance. All right, we're going to start with a sum of squares for group A, sum of squares for group B, group C, and group D. All right, so we come over here, we check it. So it's 6.8 is our mean. So we're going to just the same thing we've been doing all semester, as we just subtract the mean, we square it. And then the next group is 6.6. So it's going to be equal to B2 minus 6.6 squared. All right. Group C is 6.9. So we're going to take each data point, subtract the mean, and square it. And 6.5. Take each data point, subtract the mean, square it. All right, and this is going to give us our sum of squares. So we would divide by degrees of freedom if we were trying to estimate the variance of a population. But in this case, we only care about the variance within the group. We are solving the within group variance. So I want to know the variance of these 50 people. So I don't divide by the degrees of freedom in this case. I divide by n, right? Degrees of freedom is if I'm estimating a population. Sample size is if I just want to know the variance for this group. So I'm going to divide that by 50. Okay. So now I have four variances within each group. But what I really need is I need an overall sort of within group variance score. And we're trying to combine numbers together. Normally what we're going to do is we're going to be getting their average. So all we got to do is once we have the variance through the groups, all we have to do is get an average between all four groups. So we add them up and we divide by the number of groups, which in this case is 4. So that gives me a within group variance score of, this 2.9, right? So this within group variance score represents, this is the amount of variance in my data that is explainable by random chance alone. Or in other words, say that I would expect random chance to produce a variance of about 2.9. Right. So if the variance between the groups is substantially larger than 2.9, then something other than random chance is causing the groups to be different. The big question, how the heck do I determine the variance between the groups? Well, I have group means here. Right? I have a group mean. I have 6.8, I have 6.6, 6.9, and 6.5. I have 4 groups right here. I'm going to start by getting our average. So what I have here, actually, let's move all of this over a notch. So this is the mean for group A, mean for group B, group C, and the mean for group D. And this is what we call a global mean. 6.7 is the global mean. It is the mean of means. It's the mean of means. So I need to figure out the variance between the groups. I need to figure out the variance between the means. So here's the thing. We're going to be able to estimate the between group variance the same exact way, except now rather than using our data, we're working with means. So I'm going to take each mean, subtract the global mean, square it, add them up, and divide by the degrees of freedom between the groups, because I'm estimating the variance between the groups. So it's the exact same procedure, except I'm working with the means. So I'm going to take each mean, right? So I will take each mean, I will subtract the global mean from it, and I'll square it. And then we sum it up. And then I take my sum of squares, right? So this is the sum of squares for my between groups. So then my between groups variance of means, right? So the variance of means between the groups, right, is going to be equal to my sum of squares divided by the degrees of freedom between the, so divide by 3. All right, so this is the between groups variance of means. Okay, we're almost there. We're almost there, right? But we don't want the between group variance of means. We want the between group variance of the population. So we don't want the distribution of means. We want the distribution of the population. Get the between groups variance. I take the between group variance mean. I take this 0.27 that I just calculated, and now I'm going to actually multiply that now by n. All right. So now I'm doing the reverse of what I did with the t-score. I have to get the population variance, and I get my final value here, between groups variance of 13.5. All right, so now I have this between groups variance. I have a within groups variance. The between groups variance represents all sources of variance, all sources of variance. It represents random chance, and it represents my experimental manipulation. The within groups variance represents just the random chance alone. So now what we do is we get what's called an F score, or an F ratio sometimes, which is all we do is we take our between group variance of 13.5. I say, okay, so all of my variance comes out to be about 13.5, but 2.9 of it can be accounted for by random chance alone. That means, right, that about this 4.6, 4.7 represents the amount of variance that is unaccounted for by pure chance alone. That's my F score. And what we would do then, we come over to the F distribution, and we're going to be doing the same thing. We got to look up what our significance score is going to be. But now we have 2 degrees of freedom to worry about. We have what's called the denominator degrees of freedom and the numerator degrees of freedom. The numerator degrees of freedom is the between group degrees of freedom. The denominator degrees of freedom is the within group degrees of freedom. 3. So I had 4 groups. So my between groups degrees of freedom is 3. So I'm going to be over here in this column. Now, the denominator degrees of freedom is my within group. So my sample was 50. So I have 4 groups with a sample of 50 in each group. my degrees of freedom is actually going to be the degrees of freedom of the denominator is going to be the degrees of freedom total, or each group's degrees of freedom added together. So it's going to be 49 plus 49 plus 49 plus 49, right? So I have 50, so it's going to be 50, 100, 200 minus 4. That's going to be 196. I doubt this column goes up to 196. Goes over here to 90. That's fine. We had a lot of people, so we'll just go here to the top. But the denominator is the degrees of freedom of each group added together. We then find our alpha over here, and what we find is a cutoff is going to be 2.71. So my cutoff for 5% is 2.71. Of a data sheet, we find that our F score, so our F threshold is 2.71. We see that our F score has exceeded that. We can then reject the null hypothesis that the difference between these four groups is by random chance alone. So there is a difference between these four groups. That's the omnibus test. As you can see, like with the omnibus test, I can't tell you which groups are driving that difference, but I can say for certainty that there is a difference between these four groups. These